Hi everybody. Today we're looking at points of intersection of polar graphs. Because a point may be represented in different ways in polar coordinates, care must be taken to determine the points of intersections of two polar graphs. You know, in rectangular coordinates we simply just said set the two equations together, solve, and figure out what point or points these two curves have in common. It's a little more interesting here. So let's take a look at these two. I've got a limacon right here, and then I've got a circle over here, and you can see there are 3 points of intersection. Okay, so what we're going to do simply is go ahead and solve these in the next slide. Alright, we see r equals, setting them equal to each other, we let 1 equal this, subtracting by 1 from both sides, we get cosine theta equals 0. That means theta is equal to either pi over 2 or 3 pi over 2. Corresponding points then, r is 1, so I get 1 pi over 2 and 1 3 pi over 2. No problem. If you look carefully though on that last slide, you'll notice, hey, those 2 points are right here, right? But what about this one? That's not considered. We didn't hit that one. So what we need to do at that point in time is figure out how that happened. How come we didn't get that solution? And the answer is both graphs didn't get there at the same time. All right, and because of that, they're not solving. We can't solve it simultaneously. We just have to find the points on each curve that makes that happen. Okay, so the third intersection point is the point -1, 0 you see here. All right, on the one graph that happened at 1 pi, that's in my circle. Okay, and the other one happened, I believe, when we had -1, 0. So it's kind of a tricky piece, and you're going to have to do maybe a little tracing on your calculator and see how did I get to those points. Typically we solve to find on our we'll just solve it simultaneously like we did the first one, and then we do a method called inspection to say we just look at it and try to trace it and figure out how we got that third point, or however many points there might be. And part of the good news about this, there's a practical application. There are satellites that are going around the Earth who obviously get to the same point at some point in time, but fortunately for us and for the satellites, they don't crash into each other. That's because they're getting there at just different times. If that didn't happen, we could only have so many satellites up there, but the way they're doing it right now, we can have a number of satellites. As long as they don't crash into each other, we're in good shape. So that's kind of a practical application of what we just looked at. Okay, I want you to find the intersection points of this graph. Take a minute, think about it. How are you going to do that? And I'll pause it here for a sec, and go ahead and try to solve it, and then I'll work through it. Okay, hopefully you had a chance to kind of look this over. Here's again our functions that we're looking at, and I went ahead and put these on the calculator, and my window was from 0 to 2 pi. Again, I went by pi over 24 as my theta step. -5 to 3, and that was with considering what was happening when I'm subtracting there and taking a look at the graph to make sure I could see the whole thing here. If I take a peek at that graph, oops, there we go. You can see it over here. And you can see I've got 3 points of intersection. There's one here, and then one here. So let's go ahead and find those. First, let's go algebraically. And so if I would take this, I'd set 2 minus 3 cosine theta. Just pause here, equals cosine theta. Alright, so our next step then, 2 is equal to 4 cosine theta, if we just add 3 cosine theta on both sides, which means cosine theta is equal to 1/2. And where does cosine equal 1/2? Arms up in the air, maybe, maybe not. Cosine equals 1/2 at when theta is equal to pi/3 in the first quadrant, and its angle, its cousin in the fourth quadrant, because it's positive, it's also equal to 5pi/3. So let's take a look at that graph now. If I see it again, it's equal here and here. But this point also, and if we go ahead and just trace this, maybe get an idea. That's the point when theta is 1.5, so that's pi, and this is really 0. It's e to the negative 10th, which means it's really 0. And if I click it on my up arrow to get R2, oops, I went too far. R2 now up here, I see it there. Let's scroll back and see where that one was when y is 0. We don't really see it. It doesn't hit it there. Let's keep going around. It's at 0. We may not see it on this one with the visual inspection. But one thing that we do know is ultimately that point looks like we might be, well, it's hard to say. I think if I solved it, it's the inverse cosine of 2pi/3 if I go back to that. But obviously that is a point. The point itself is 0, 0, and that's what we just go ahead and put in. All right, so we go back to this. So theta equals pi/3, and that happens, so I've got the points 1/2 pi/3. One-half 5pi/3. And the point 0, 0. Okay. All right, let's see what's next. Now we're going to look at the arc length in polar form. And so this doesn't look too different from what we've seen before. And here's our formula. The integral from a to b of the square root of, we're familiar with this, the function squared plus its derivative squared. Okay, we didn't really derive this formula, I guess, so just have you look at that. And here's another way to look at it as well, alternate way if you'd prefer. So we'll come back to this formula. Let's go ahead and find the length of the arc from theta equals 0 to theta equals 2 pi for this cardioid. All right. So let's go ahead and set that up. We've got the integral. We see in this case that first let's go ahead and say, let's go back to the formula. I need the function squared, I need the derivative squared. So let's do each of those first. So r is equal to 2 minus 2 cosine squared, cosine theta. R squared is that expression squared, which is going to be, I didn't need the parentheses, put them in there anyway, 4 minus, and 2 times this is going to give me 8 cosine theta plus 4 cosine squared theta. Okay, that's r squared. We also need to know what is f prime of theta or r prime. We want to look at that. So r prime, if you would, or dr d theta, or f prime, however you want to look at it, is simply equal to 2 sine theta. And that squared, r prime squared, is equal to 2 pi. 2 pi is equal to, it's just 4 sine squared theta. So now all we're going to do is take that integral, since we're going from 0 to 2 pi, of the square root of r squared, which happens to be right here, or minus 8 cosine theta, plus 4 cosine squared theta, plus this expression squared, or this expression, which is 4 sine squared theta, d theta. And now we would maybe get some simplification here. I think we can see that that would be a 4 here, and another 4. I'm going to get 8 minus 8 cosine theta. But we can go ahead, if you want to simplify that, using the trig identity, the Pythagorean trig, you can. Otherwise, you can simply crunch it into your calculator and come up with a solution. All right. All right, our final part for this section is talking about area of surface of revolution. And we've got parametric equations, x equals r cosine theta, y equals r sine theta. And here's our theorem and our formula. F is a function whose derivative is continuous. Area of surface formed by the revolving this around r equals f of theta, from theta equals alpha to theta equals beta, about the indicated line, is as follows. And these look fairly complicated. You can see this is just what we just got done doing, talking about arc length. We multiply it by the function and then sine theta if it's going around the polar axis. We multiply that expression by f of theta times cosine theta if it's going around the line theta equals pi over 2, in other words, a vertical axis. So here we have the problem. Find the area of the surface formed by revolving the circle around r equals f of theta equals cosine theta, about the theta equals pi over 2. So we're going to use that second equation. If I look at this and I say, here's r cosine theta, it's going to take on all its values, the whole circle, between 0 and pi. We look at this figure, it's called a pinched torus. Some of you may look at that and think a donut. We can put some sprinkles on top if you'd like. It looks pretty good. Maybe some other stuff. Alright, so how are we going to set it up? Well, we can use the second formula. And so I get s equals 2 pi. Instead of alpha and beta, we're going to put 0 to pi. And we're using cosine, and my function was cosine. So we simply get here, cosine times cosine is cosine squared. The square root, this expression right here, of course, the Pythagorean trig identity is just 1. So now I've got 2 pi times integral from 1 to pi of cosine squared theta d theta. If we look at this, it's the formula. We can use the trig identity and identify this. You'll notice the 2 has disappeared as well. There'd be this over 2, but we multiply it by the other 2. So that disappeared. You could also go directly from here using your calculator to find out the answer. That is going to give you pi for your answer right in here. And so my final answer is pi squared. And we are finding the surface area, so that would be units squared. All right. That should end it for chapter 5, or chapter 10, excuse me.